All right, so let's get started. So, like I told you, we just relook at the exams. So let's do today. Oops, I forgot my red. I took the red for grading, so now I don't have it. So it doesn't matter. So example. Over here, this is basically a combination of what we've been doing from the beginning of the semester to what we just did at the end. So we're gonna have over here we're gonna have a beam. I think this one is okay, so here we go. All right, so let's make sure here is clear. This will be fixed over here. We're gonna have that the length so let's first do this one. Y and X. The length of the beam is going to be 2 meters. Thickness of the wall is going to be 2 millimeters. B1 equal B3 equal B4 equal B6 equal to 650 millimeters square. B2 equals B5 equal to 1300 millimeters square. Then this time, since we're going to be calculating deformations, we need to have some material properties. So we have the modulus of elasticity would be equal to 69,000 newtons per millimeter square. And G will be equal to 25,900 newtons per millimeter square. Okay, and let's see what we have over here. Will be that we have the loads 1, 2, 3, 4, 5, 6. And here you have a force Vy equal to 44,500 newtons applied. So this is important at shear center. So let's see, why is that important? What does that mean? If it's applied to shear center, this is an important part. What does that mean? It will be no torsion. Basically, this structure will just be bending up, no? Mm-hmm. Okay. All right. So will be no torque or anything about the structure. Correct? Mm-hmm. That's important here. Okay. So T is the thickness of all the panels. And let's see, we know some distances here. So I think this distance will be 250. I think this will be millimeters. So this will be in millimeters. Here the distances 250, 250, and 500. So the question is to determine the vertical deformation at the free end. Okay, so basically, in here, what's going to happen? I mean, we're going to do the complicated way, but if you do want to yes, go ahead. Sorry, I think it's the other one, the first one on your side. Oh, no,
Okay,
is that better?
Yeah.
Perfect. Yeah, sorry for that. You should just let me know. Okay, so basically, what's going to happen? This load over here is going to produce. What type of load is that going to produce on the beam or the wing over here? It's going to produce bending, but also we're going to have shear on the panels, correct? Okay, so here I think it makes sense. Which one do you think should contribute more to the deformation of the free end? The bending or the shear? You think the shear? So you think what's going to be influenced more the deformation here? The bending moment or the shear flows? Okay, so that's what we're going to be solving, no? Okay, it's going to be the bending moment. Right? And it should be by line. Because when you look at the shear flows, it should affect something, but not that much. All right, I mean, we will see.
Yeah, okay.
Okay, so anyway, but let's show it and do it. Okay, so over here first, let me ask you a couple of things first. So this problem is what? Statically determinated or statically indeterminated? Indeterminated because we have more than one cell, no? So what does that mean? That we're gonna have to do the steps 1, 2, 3, and 4, correct? So we need to do step 3, which is the additional equations. I hope that by now those steps are clear. On the exam, I think the exams were all very good with the procedure, okay? Which is what I did get. Right? Okay, so then we say that Vy apply a shear center. So what does that mean? No rotation or pure bending. It has an E here, pure. Okay, and we're going to say over here that the deformation at free end should have one component due to bending, as we discussed, so bending moments. So let's say M's plus the shear flows Q. Okay, so let's say that the deformation doesn't matter, it would be the same at 1, 2, 3 would be the same, but let's say the deformation. So maybe let's say here recalling from the notes. Okay. Let's see the question here. What is the other thing that we need to be careful when calculating deformation? What needs to happen? Remember, what is something that is crucial? What is crucial over here? Is that you need to have a force at the location where you want to calculate the deformation, no? So if this is applied at the shear center, you agree that any point over here will move the same. Okay, so let's say if you want to apply a force at 2, it's fine, but what about we could just use here Vy, no? Okay, the force, so we calculate Vy, will be the deformation at the so this will be deformation at shear center. Okay, where what is the name that I give to you? What is that strain name that I give to you? Look at the notes if you want. I call that, that should be on the title of the chapter. It is, what's the title of this section or chapter? It is Principle of Virtual Work and Strain Energy. Okay, remember this one was equal to what? Sigma epsilon squared dV. All right, so two, if you want, substituting U into the Q sub I expression, we're gonna get what? Q shear center will be equal partial U partial Vy. This will give you integral 0 to L. Again, we did derive all these expressions. M sub I over EI times partial M sub I partial Vy dz plus integral 0 to L of circular equation Q sub I over GT partial Q sub I, oops, yeah. Partial V sub I ds dz. Okay, so again, I don't have it red over here. Maybe I could go get one. This would be the total deformation. This would be the deformation due to bending. And this will be the deformation due to shear force. Okay, does that make sense so far? All right, so if you want part A, we're going to call this part A will be deformation due to bending moments. So again, you will see that this is pretty simple and it gives a pretty good answer. And then when you do a lot of work, just to add something. So let's see. So let's call this one Q sub A, let's say bending, okay? Will be the first term, which is integral 0 to L M sub I over EI partial of M sub I partial dy dz. Okay, I'm gonna do here a little figure of our problem, but if you want, this will be a side view, okay? I'm gonna do a side view of this beam. So it will look like what? We have here, this will be the length of the beam, subjected here to Vy, and this will be the length L. Okay, what would be the form of the bending moment? I mean, you did that on the exam, so what should it be? Should be maximum of the root, no? And it should be 0 over here, okay? At 0 at the end. Perfect. So now my question is that what is the expression for the bending moment? So it is Vy, correct? So remember, we start from here, no? Z start from here. So what should it be? Vy times L will be here, but it needs to be 0 at the end. So what do we need to do? This should be Vy times L minus Z. So why do we need to give the moment? Not like before, where we were just finding the moment of the section. We need to find the equation because here we integrate with respect to Z, no? With respect to the length. We find what is the deformation due to all this applied moment along the length of the wing or the beam. Okay, so over here I'm going to say where M sub I, okay, will be equal to M, will be easier, will be equal to Vy L minus Z. So then what would be partial of M with respect to Vy? That would be equal to what? Just L minus Z. Okay, so now we just do substituting into Q sub A. We're gonna get what? Q sub A is equal to the integral of M over EI partial M partial Vy dz. This was gives you integral 0 to, so 0 to L, 0 to L of M, which is Vy times L minus Z divided by EI times L minus Z dz. If you do the integral, you get here 0 to L Vy over EI L minus Z square dz. Oh, I forgot maybe. Okay, we did not calculate it yet, so that's why I cannot do it. So this should be the bending about which axis? About which axis is that bending? Which one?
X.
It's bending about X, no? Yep. So once we do the calculation, I is really equal to IXX, all right? Okay, so now we could just go and substitute the values, but I like to keep it symbolic because when you keep still symbolic, I can follow what you're doing. If you start putting values, it's hard to follow values, no? So you see, half a page. Really, the problem could be done in half a page, and you will have a pretty good answer. All right, 3. So part B. Deformation due to shear flows. So in that case, let's call this one Q sub B. Is a second expression 0 to L. Integral of Q over GT, partial of Q, partial of Q, ds. dz here, really the Q is equal to what? Is equal to our Vy, okay? And remember here that the Q's refer to shear flows. All right, so let's go. And before we do this calculation, maybe you should have done that at the beginning, but since I forgot, let's do it now. Cross-section properties. So basically what we need to find is what? Ixx. So let's see if I do a figure here. Let's see what do we have. 1, 2, 3, 4, 5, 6. This would be the natural axis from where the y are calculated. Okay, so in this problem, what do we have? We have y1 equal y2 equal y3 equal to what? What was the thickness from the initial figure? Or the depth of the wing is 250, no? So what should be our y? Half of it, no? 125. And y4 equal y5 equal y6 will be equal to minus 125. So this is symmetric, okay? So the CG will be located in the middle, but it's not going to affect the IYY. So we'll have, the IXX, we'll have IXX. The giant expression is y squared dA, but we know that we can approximate that. I mean, we can calculate that in our approximation by doing the B sub R's y sub R squared between 1 and 6. Okay, so you know this is B1 y1 squared plus B2 y2 squared plus the same thing up to B6 y6 squared. And if you do the calculation, you find IXX equal to 81.25 10 to the 6 millimeters to the 4th. I mean, if you have any questions, stop me, but I'm pretty sure all this stuff is pretty clear. So if you remember, what is the stuff we are doing in our head, we need to start thinking that what we're trying to solve, what we are solving is, let's see, 1, 2, 3, 4, 5, 6, to be equal to what? All right, so let's see if I can do that. Okay, and what should I have over here? Here I should have the Q's, and this will be the Q bars, no? So you will have Q bar basically equal to Q plus Q12, whatever that is. Okay, so what did we say at the beginning is that this problem is statically indeterminate. So here we go. So step 1, which is equivalent of doing what? No, so finding the summation of forces. It's important to know that, okay? But in order to do that, what do we need? So make cuts. And evaluate shear flows. Okay, so recalling the equation for symmetric, and what do we have here? Vx equal to 0. You remember that equation? We use it a lot. What is that equation that I have in mind? Q will be equal to what? V sub r, y sub r, no? Okay, you have used it enough. So in order to use this equation, what do we need to do? We need to have a starting point. So in this case, our starting point, we need to make 2 cuts. We need to make 1 cut on each cell. All right, so 1, 2, 3, 4. So, okay, so let's do another figure here. Showing our cuts. We have what? We're gonna have Q 1, 2 equal to 0. Q2, 3 equal to 0. We know this is the natural axis from where we calculate the y's. We know that distance here is 500, 250, and on this side is 250. Okay, but really we care about plus or minus 125, no? So in this case, what do we have? We have, so let's recall the equation, which is Q equal minus Vy over I xx Br y sub r. So we know Q12 equal to 0. Q23 equal to 0. So I go around, okay? First I go around 1, 2, 0, 2, 3, 0. I go to 3, 4. Q34 will be equal to what? Q23 minus Vy over Ixx B3 Y3. Okay, so if we do that calculation that you know how to do now, you get minus Vy over 1000. Okay, you could do a calculation, or you can do it by symmetry, but Q45 should be equal to what? Q34 minus Vy over Ixx B4 Y4. What should we get? If you look at the symmetry, this one is 0, this one should be 0, no? So we should get 0. Then we go 5, 6. Q5, 6. So this one will be, let's do first Q25, otherwise we're going to run into a problem. Q25 will be equal to what? Will be equal to Q12 plus Q23. Okay, I'm going from here to here. So you have Q23 go in minus Vy over Ixx B2 Y sub 2. And if you do that, you get minus 2 times Vy divided by 1000. Now I can go to Q56. That would be equal to what? Q45 plus Q25 minus Vy over Ixx B5 Y5. But if we did that correct, what should we get? If you look, it needs to be symmetric to Q12, so that should be 0. And then Q61 will be equal to what? Q56 minus Vy over Ixx B6 Y6. And this will give you, as well by symmetry, minus Vy over 1000. But we do the calculations. So if I redo here a figure, let's see what we have. We have 0 here, 0 over here, 0 over here, 0 over here. Then let's see, 3, 4 is actually going up. Vy over 1000. 1, 6 is actually going down. Vy over 1000. And then what else do we have? And here 5, 2. So 2, 5 will go from 5 to 2. 2 Vy over 1000. Yes.
Would cutting it in different on different flanges, would that stop certain interactions from happening with the other shoes?
No, you can make the cuts any way you want, but this value will be different.
Yeah.
I mean, these expressions will be different.
Okay.
Yeah, no, it doesn't matter. I mean, what happens is that you need to make cuts on each one of the sides. So you make the cut, let's say between 2 and 3, and 3 and 4 is not going to work. Means you can make the cut, let's say between 3, 4, can make, let's say, the cut instead of doing here between 1, 2, and 2, 3. Let's say you make it between 3 and 4 and 1, 6, it will work.
What about one cut on 2, 5?
No,
No?
no,
Okay.
it will not work. All right, so that was step 1. So what is step 2? This is the one you were saying before. This one is equivalent of doing what? Summation of moments equal to 0. So what do we need? We need to determine Q1 and Q2. And in order to do that, what do? We equate, let's say, external okay, so in other words, what do? We do summations of external equal to the summation of internal. Oh, now I remember this one. Don't leave now because you're going to miss the most important part. So, all right, so let's say over here, just randomly, I'm going to say, let's say we take it about 0.4, okay? All right, so let's say I'm going to redo the figure here. Okay, here I'm going to start adding some stuff, but area 1 will be equal to what? So this is will be equal to, let's see, S23 times S34. This is 1 over here, panel 1, panel 2, and A2 equal to S12 times S, let's say 25. So over here, this is important part. Now you will say, okay, we can just go and do the summation of the moment of, let's say, the summation of the external moments about 0.4. So we know the force Vy. What will be the arm? Do we know the location of the shear center? We don't know the location of the shear center. We have not calculated. So one option to solve this problem will be what? To go and first solve the location of the shear center. Okay, but then what do you do with the shear center? So in other words, before, what were we doing? Let's say you had that distance. What is the normal procedure? You get one equation from step 2, no? Summation of moment external equal to summation of moments internal. But you have one equation, you have two unknowns. That would be, what would be your two unknowns? Q1 and Q2, no? Correct? Then we needed to go to step 3, which is what? Find the location, find the additional equation. In order to find the additional equation, what do? We say that the angle of twist of these two must be equal to each other. Okay? And that was giving us two equations in order to be able to solve for Q sub 1 and Q sub 2. Yes? Okay? Because this was, if you want, twisting, no? Okay? In this case, we don't know the location of the shear center, which we could calculate. But in order to calculate, I mean, we would be the same thing as find the location of the shear center. So basically, we need two equations. All right? To solve for Q sub 1, Q sub 2. What can be those two equations? What do we know about the angle of twist?
0.
At the shear center, it should be 0.
Yeah.
So now, instead of equating the shear center of this one to this one, what can we say? Shear center of this cell must be equal to 0, and the shear center of this one must be equal to 0 as well, no? So that will give us two equations, correct? Okay? All right, so that's what I'm gonna write down now. Okay, so following the normal procedure, comma, the location of the shear center is required. However, in this example, since the shear force Vy is applied at the shear center, the example can be solved as saying what? Vy at shear center, which means what? No torsion, no twist. So what does that mean? We have d theta dz of cell 1 will be equal to 0, and we'll have to d theta dz of cell 2 equal to 0, where d theta dz equal 1 over 2a So basically, what are we gonna have over here? This will be our equation Roman 1 and equation Roman 2. So this will be the two equations that we have in order to determine Q1 and Q2. Did you understand what happened here? Does that make sense? Okay. Yes.
So if the forces aren't, or if the force doesn't go through the shear center, you can apply this and you have this off the shear center.
If the force what?
If the force doesn't go right through the shear center.
I mean, if you know the location, yes, then you need to use the
then
normal
you have
procedure.
to do it, okay.
Yeah, because you will know where the force is applied.
Mhm.
You could also solve this problem by first finding the position of the shear center. But how would you find it? Doing exactly the same thing by doing this.
Right, we're just,
But your unknowns will be, remember as we did dy and dz, will be vz. When will be that distance here. Okay. All right, so here we go. So we need to find out what is the expression for Roman 1 and Roman 2. So maybe let me redo a figure because this is always the location where if I do a mistake, it's in this step, and I think it's the same thing with you. So let's redo the figure. Remember, the bigger the better, the bigger the better. So let's see, where's my previous page? Here it is. So we have over here, we have the Vy over 1000. So this is really the Q61. Then we have Q34 Vy over 1000, and we are over here Q25 2Vy over 1000. I'm gonna have enough stuff to put on that figure. So here we have Q2. Here we have Q1. There'll be too much on this figure. Well, that's what it is. And remember, all the other shears here would be 0, 0, 0, and 0. So this will be our cell 1, our cell 2. Okay, so if you remember, when we do the angle of twist, so let me rewrite the equation here. We have d theta dz equal to 1 over 2a integral of q over gt, and we go around the cell, we call that ds. So let's do maybe here cell 1. So what we're gonna have d theta dz of 1. And remember, when we do the angle of twist, this is like taking moment. So let's say you can do that in your head, but let me just put it. Let's say we go counterclockwise, positive. So in this problem, everything is made of the same material, so we can kind of factor the 1 divided by 2 a sub 1 gt. Everything is the same thickness. Okay, so now before I forget, so I'm here on this cell. Okay, the cell 1 is the one that is defined by 2, 3, 4, 5. So I can say what? Q1 is going to be acting over which length? S23 plus S34 plus S45 plus S, I don't know, I call it 2,5 or 5,2, let's say 5,2, it doesn't matter, or 2,5, don't care. And with this moment be positive or negative? I mean, this angle of twist. will be counterclockwise, no? Yeah, this one's going counterclockwise. So it will be counterclockwise. Now we need to pay attention to what is this moment, the moment 3, 4 going to do. What is 3, 4 going to do? Is that one going to create the cell to go on the clockwise direction or counterclockwise direction? This one over here. It's going to make it go clockwise direction, no? So now this will be negative. So if you want minus the Vy over 1000, which is really what? This term is really Q34. All right. This one will be acting over which length? S34. Okay, since I'm doing this one, I did one by one before I forget, because I almost forgot it. What do we have acting over 2, 5? You have this one over here, but also the Q2, no? So let's go here, but Q2 is also acting, oops, what did I put here, 3, 4? This should be, oh no, this is correct, okay, no, I'm good, I don't know what I'm doing here. Okay, now let's look at 2, 5. So what is acting over 2, 5? Over 2, 5, we're gonna have Q2 and the Q25, no? The Q25 will make this to go what? Clockwise or counterclockwise? Q25 will make it go counterclockwise, but the Q2 will make it go what? Clockwise, no? So you want here, I could put plus, in case otherwise I'm gonna have to rewrite it, minus Q2 plus 2 Vy over 1000, which is really Q25, and these 2 times S25. And this should be equal to what? 0, no? Okay? Do you understand this equation? That's generally where you do the mistake. And myself as well, okay? I'm gonna be honest with you. This is the step that I need to write it down, okay? So let's say cell 1 here, we write d theta dz of 1 equal to 0. We do the same thing here for cell 2. So this will be our equation 1. Cell 2 will have d theta dz of 2 equal to 0. So this will give us what? D theta dz of 1 divided of 2 A2 GT. Okay. So let's try to follow the same structure as we did with the other one before. So we first look at what is the Q2 going to do. It's going to go along all the members. So it's going to be Q2 going to go through, let's say, S12 plus S25 plus S56 plus S61. Okay, now let's do this one. I'm going to follow the same order. The Q61 is going to make cell 2 go clockwise or counterclockwise? 61 is going to make it go clockwise, no? So it will be minus Vy over 1000 times S61. So remember, this is Q61. And now we'll do the same thing as before. I don't know which one will be positive or negative, but if I do this one, now I'm going to do the whatever is on top of 25. So 25, we have Q1. So Q1 goes up. So it's going to make the cell 2 to go clockwise or counterclockwise? It's going to make it go clockwise. Q1 will coming up here. It will make this bend clockwise.
Okay.
Okay. So everyone will be the same thing as before, minus Q1. And now this one will be what? Q25. We make the cell 2 go clockwise or counterclockwise? Clockwise. So it will be negative again. Minus 2Vy over 1000 times S25 equal to 0. And this will give us the term 2. So let me go back for a second to the notes to clarify, because I want to make sure we follow the procedure. Okay. Okay, guys, just to make sure that we follow the procedure, can we add over here? Maybe, let's say this will be step 3. Okay, I like the steps, okay? When I like to teach something, I like to teach steps. All right, so now, so I can come over here. And now what can we do? So solving equations Roman 1 and Roman 2 for Q sub 1 and Q sub 2. We're gonna get Q sub 1 equal to minus 1.3 10 to the minus 4 Vy, and Q sub 2 2.17 10 to the minus 4 Vy. Okay, here I could give you values because we know Vy, but I don't have those numbers. Remember Vy was given to be equal to 44,500 newtons. So if you want, you could solve Q1 and Q2. But obviously I did that with MATLAB. Okay, so finally, we will go to step 4. Which is solve for the final shear flows. So Let's do again the figure. The bigger you do the figure, the better. I always said. So I think I remember these ones. Those will be Vy over 1,000. Vy over 1,000. Two Vy over 1,000. Then we have Q1. So Q1 here, we know it's negative from before. So that what does that mean? It means that it goes clockwise with a magnitude of 1.310 to the minus 4 Vy. What do we know about Q2? Is positive. So what does that mean? It goes counterclockwise. And here I'm just looking at the magnitude, 2.1710 to the minus 4 Vy. Remember here, I'm just looking at magnitudes. Okay, so remember we defined before the final shear flow will be equal to Q plus Q1 or Q2, but you need to be careful with the sign. So I don't know, maybe let's do just a couple of them and then I give you the values, and this is 0, 0, 0, and 0. So in this equation, what should be Q12? Q12 should be equal to what? To the Q Roman 2, no? Because Q12 is 0, no? And this is equal to what? The 2.1710 to the minus 4 Vy. I don't know why I don't have the values, but all right. I know, but I did not calculate it. I could give just the value, but then Q23 should be equal to what? Q1. So I say that will be 1.310 to the minus 4 Vy. Now Q bar 34 should be equal to what? Okay, but if you want, will be Q34 plus Q1, but is it going to be positive or negative? It's going in the opposite direction than 3,4, no? It's going to go up. Yes? So you can put it here or do it on the figure. Personally, I'd rather do it on the figure, but if you write the equation, now this should be, oh, so wait, if we do it that way, yeah, so 1, 2 is positive, 2, 3 will be positive, this one will be negative, so minus, this will give you 1.13 10 to the minus 4 Vy. Then Q bar 45 would be equal to what? Wait, let's go back for 1 second, guys, because I don't want to confuse here the signs and so on, because Q12 will be positive. Q23, if we do it this way, will be negative. Okay, let's follow the number sign convention. It will be going in that direction. Then Q34 will be going from 4 to 3, no? So it should be negative. Q45 will go from 5 to 4, so it should be minus Q sub 1. should be equal minus 1.3 10 to the minus 4 dy. Now let's do the middle one, which is, I will say the conflictive one here. Q bar 25 will be equal to what?
Be plus Q2 minus Q1.
Yeah, but it will be it's going from 5 to 2. So it should be really minus 2 Vy over 1000. Then what? Plus Q1 plus Q2. No, minus Q2. Wait.
I thought Q1.
25. No, 25 is going down. So this one is going opposite. So Q1 is going from 2 to 5, and 25 is also going from 2 to 5. So if you do this gives you Q bar 25, 1.65 10 to the minus 4 Vy. Then Q bar 56 should be equal to what? Q2, which would be 2.17 10 to the minus 4 Vy. And finally, Q bar 61 will be equal to what? Q2 plus Vy over 1000, which should give you 1.22 10 to the minus 4 Vy. Okay, so why did we do all of this work? We did all this work in order to find what is the deformation due to the shear flow. So substituting into the equation that we had before, Q sub B equal to what? Integral 0 to L of the circular integral of the Q sub R I sub I GT partial Q sub I partial, oh, sorry. That's why we did not substitute for Vy. You see, there is a reason I say something not appropriate before it, because we need to take now the partial derivative of the shear flows with respect to Vy, ds, and this will be dz. So if we do the calculations, so I'm not going to do, so obviously you need to use a computer, you can do it by hand, but it will take you a while. This will be equal to what? 0 to L equal 2000 millimeters times 1 over GT, that this is constant, times the circular integral, that would be equal to what? Q bar 1, 2, partial of Q bar 1, 2 with respect to Vy times S 1, 2. I do one more, plus Q bar 2, 3, partial of Q bar 2, 3 with respect to Vy, all the way to the Q61. You understand this equation here? Okay, I'm just substituting. I'm doing here the Q bar times the partial Q bar with respect to Vy, I factor out by the GT. If you do this calculation, then I will highly recommend to do it with MATLAB. You get that QB equal to 13 Vy divided by 238,280. And this will be the deformation.
It's 238,000.
238,280, yeah, 238, yes. So basically, this is kind of combining everything we have done so far, no? So finally, probably we'll finish a bit early today. Nothing wrong with that. 8. So the total deformation is, let's say, Q total will be equal to Q sub A plus Q sub B. So in other words, Q total, if you look back, we said that Q sub A was equal to Vy over EI L minus Z squared dz plus the one we just did, 13 Vy divided by 238,280. So if we had to integrate this one, we can do it with equal to what? Vy divided by 3 EI L minus Z cubed plus 13 Vy, 238,280. And once you do the substitution, so basically, what do we have? We had, what was the calculation we had? E was going to be equal to 69,000. So be careful here. Yeah, 69,000 newtons per millimeter square. I was equal to IXX. What was that equal to? (81.25 10 to the 6). And dy, I think, was equal to 44,500. Okay, so with this data over here, we should find Q total will be equal to 21.17 millimeters plus 2.43 millimeters, which gives a total of 23.59 millimeters. So last thing over here. So this term over here represents what is the bending due. So what is the deformation due to the bending? Okay. So remember, this is bending. This one here will be shear flows. Okay. If you do a calculation of what is the percentage, what is the what does the 21.17 represents out of the total deformation? That is about 89.7%. And then the shear flows will be what? About 10.3% of the total deformation. Okay, so probably we don't have the time, but what would be something good for you to do about this problem? Probably go and do the FIMAP, no? Okay, what happens is that it's going to be a little bit of a nightmare because you're not going to know the position of the shear center, no? But I mean, maybe it's not going to affect it that much, no? You just calculate it and then you need to apply the force at that location. But let's put it this way. In real life, do you think the force is going to be applied at the shear center?
No.
No. So, you know, all this stuff is basically for simplification, but in real life, it's going to be somewhere, no? Okay. So this is basically, you know, like I say, if you know how to solve this type of problem, this summarize all the knowledge that I want you to learn during the semester. Okay. So probably today we do one more example about something. I'm uncertain of what. And then Wednesday, probably if you want, we can spend some time. Doesn't mean I'm going to do it. It means that I will come to class and I will give you time to do it. And I'm going to answer some questions to give you time about the project. Okay. And Thursday we figure something out. Is that okay?
Yes.
Okay. To talk about the exam 2. So I kind of read it, but what I'm going to do, I'm going to revise it and base the grades on problem number 2. Most of it, okay? Most of the grade will be in problem number 2. All right.
I'm assuming that I'm a grade before speaking of that.
Yeah. The exam you're going to get it back. I have them here, but except for one of you that uploaded pictures. So I'm not able to print pictures.
Yeah, no, I so when I was uploading on Canvas, I tried scanning the PDF and uploading those pictures, and I have no idea why.
Okay, so I cannot print it. The other thing you understand is like,
Yeah, I can email you pictures if you want.
no, I'm not going to go and print one page at a time.
No, I'm saying I can take the PDF and I can email it to you as well. Just
Okay, if you want to do that, and maybe I can write something down because right now I just provide a grade. Don't look at your grade because they're probably going to change. They're probably not going to change that much. But look at grade, but you don't have any comments because I don't have anything to write on, okay? And you were not the other one. Somebody else did the same thing. Okay, so any question about what is expected for the rest of the week? Everything clear? Any suggestion? No? I mean, my suggestion would be, if you have time this afternoon, what about you do very quick a final element of this and just put, even if it is the force on whatever, on node 2, and see what it gives you. Okay? If you want, okay? I want you to get used to validate whatever we do. All right, see you tomorrow.
I don't.